and we'll go ahead and move on to our next, resilient computing.
All right, great. Thank you. My name is Brock Lemires, and I'm a professor of computer engineering at Montana State University and the founder of a venture that I'll be talking about today that's called resilient computing. So the purpose of resilient computing is to provide radiation-tolerant computing solutions for the aerospace industry. And I founded this venture about 6 months ago as a way to commercialize computer technology that's been being developed in my MSU research lab for about the past decade. The unfair advantage of this venture is that we are building space computers, and space computers are all about what we call flight heritage. Flight heritage refers to that a technology has actually been proven in space. And spacecraft developers will not choose a technology unless it has flight heritage because it's too risky. Space technology companies spend millions of dollars and many years trying to fly their technology to get flight heritage so that it can be adopted. But our computing technology has achieved flight heritage through over $5 million of funding from NASA to MSU to conduct this research. Resilient computing will have an exclusive license with MSU for this computer technology, and after 10 years in development, it is ready to start being commercialized. But the question is, why do you need a new type of space computer? In the next decade, you're going to see an explosive demand for increased processing on satellites to handle the massive amounts of data generated by new imaging sensors and communication systems. Now, our Earth-based computers can handle this processing, but they can't operate in space due to radiation. Space radiation causes the computers to continually crash. Now, the aerospace industry has come up with a technique to prevent these crashes called radiation hardening. That's where they go in and they modify the underlying materials of the computer. The problem is that this technique causes these computers to be expensive and slow. As a case in point, the most popular radiation hardened computer is the RAD750. This was used on the Mars Perseverance rover that just landed on Mars. It costs $200,000 and it can only run at 200 megahertz. It was also used on Mars Curiosity a decade ago and came out around 2002. So the most cutting edge radiation hardened computer that we have is 20 years old. Our solution is called RadPC. So in RadPC, instead of trying to prevent crashes from radiation by modifying the underlying materials, RadPC expects the crashes to occur and uses proprietary software procedures to elegantly recover from them. This software approach makes RadPC actually more resilient to radiation and scalable to different hardware platforms. We implement RadPC on a commercial off-the-shelf programmable device, and that allows us to track the cost and performance of Earth-based computers. RadPC has achieved flight heritage through NASA funding on high-altitude balloons, on sounding rockets, on a 12-month mission to the International Space Station, and on 2 satellites that are currently orbiting Earth. In 2023, RadPC will go to the moon as part of Artemis, and we will achieve lunar flight heritage. The number of computers that can claim that can be counted on one hand. So the question is, why is now the right time for this venture? The answer is because low Earth orbit is being commercialized. Low Earth orbit refers to the easiest to reach and best understood orbit around Earth. And that's where our space station is, and that's where most satellites are. About a decade ago, NASA retired the space shuttle, and they began efforts to turn over access to low Earth orbit to the commercial sector. NASA pumped billions of dollars into companies like SpaceX and Northrop Grumman so they could develop flight capability so they could shuttle astronauts and put satellites into low Earth orbit. And this investment is coming to fruition right now. SpaceX just conducted its first commercial crew delivery to the space station, and now all US cargo that goes to the space station is ferried there by private companies. This year in 2021, if all the predictions come true, we will finally top the record number of launches set back in 1967. It took 55 years to get back to this level of space access. So while low Earth orbit is being commercialized, NASA is focusing on deep space. That's the moon, Mars, and beyond. But everything that goes into outer space needs a radiation-tolerant computer. If you look at the number of spacecrafts being put into orbit right now, it's hitting an exponential. So when you look at the market size, we look at the small sat market. A small satellite is defined as less than 180 kilograms, but it really represents every satellite that goes up. Almost every satellite is considered a small satellite. So the commercial small satellite market, which is like imaging systems, communication systems, it is expected to grow to $7 billion by 2025, up from its current value at $2.8 billion. To put that in perspective, In the last decade, humans have put about 1,500 satellites into orbit. In the next decade, we're going to put over 8,000. That's a 600% increase. And in all those satellites is the need for radiation-tolerant computers. The radiation-tolerant electronics market is expected to reach 1.7 billion by 2026. And in addition to the commercial sector, there's the Department of Defense. The Space Force has over $10 billion allocated this year alone for space technology development, including radiation-tolerant computers. Resilient computing will have two lines of products. First is software that will be plugged into existing design tools that will allow spacecraft developers to implement their programs on the RadPC architecture and implement it on their own programmable hardware. Now, we will tell them that they need some different hooks on their hardware, which we'll share and they can implement. But if they don't want to build their own hardware, we will also sell hardware that can implement the RadPC architecture. This board right here has been developed at MSU, and we have it for sale on day one. The competitive landscape for this market is two ends of a spectrum. On one end is the super expensive, highly reliable, but slow radiation hardened computers like the Rad750. On the other end is the non-radiation protected computers that are very inexpensive, but they crash continually and cannot be used in critical operations. RadPC will live in the middle of this, where we will provide increased computation, increased reliability at a better cost point for the commercial sector. Our high-level financial projections consist of three components. The first is, since Resilient Computing is a technology company, we will be competitive for SBIR and STTR grants. In fact, 10 days ago, I was notified that Resilient Computing won a NASA SBIR Phase 1 grant. We were only one of three companies to win in this round of SBIR funding, and we're the only first-time awardee in Montana. You can see that the blue is the grant revenue. It will go up as the phases of the SBIR program as we move through them. And it'll always probably be a component of our revenue, because that grant money can really fund the cutting edge research that's needed for this venture. The second component of our revenue are DoD contracts. We have already been contacted by companies such as Raytheon, Boeing, and agencies such as the Air Force and Homeland Security about building custom RadPC variants for their applications. We call these cost plus contracts because they will pay for the engineering design time to design the RadPC variant, in addition to committing to a certain number of orders of paying for the material cost plus a markup. This is important because this keeps your engineers employed while you roll out the most important part, which is the product sales. The RadPC for the aerospace market, if you think about units, the average is about 3 computers per satellite. So you're talking about over the 2,500 computers per year. We believe RadPC can actually achieve as much as 20% of the small satellite computer market right now. And what's more exciting is that RadPC for aerospace is the hardest one to do. And that took all the funding from NASA and all the funding right now to get going. But once you have it established, you can move into a larger market, which is called critical infrastructure. This is the electrical power grid, water treatment plants, the communication networks. This market is massive. There's literally hundreds of millions of embedded computers that all need fault-tolerant computers. So once you establish RadPC for the aerospace industry, you move into critical infrastructure. This is millions of computers sold each year. And if we could even capture 0.5%, that would lead to an additional $5 to $6 million of product sales per year after we get through years 5 and 6. To pull this all off, our team right now consists of myself as the Chief Technology Officer. I'm the principal investigator on all the money that's come from NASA to develop RadPC. And I have recruited Kendra Cook, who works for NASA's Jet Propulsion Laboratory. Kendra has over 18 years of experience working for the DoD and NASA, and is a former Air Force officer. She brings expertise on how to turn technology into solutions for the DoD and the Air Force. And most importantly, she knows how to navigate DoD contract vehicles. And finally, the engineers for my company will consist of students recruited out of my lab at MSU. This gentleman down here on the right is Chris Major. He's my current PhD student. He is actually the principal investigator of our NASA SBIR Phase 1 grant that we just won. And with that, I will answer any questions that you might have.
Thank you, Brock. Thank you. Really nice presentation. Okay, we'll go ahead and have you unshare your screen, and we'll get our judges up here. And who would like to go first? Rick will go first.
Hey, Brock, great presentation. Thank you. Extremely interesting technology. Give me a little sense on, Obviously, it sounds unique and differentiated. How do you protect the technology? I mean, if you're an investor looking to invest in this, how's the technology protected from all the big mega companies that you've outlined there as potential customers and or competitors?
Yeah, great question. There's kind of three levels. So we currently have a provisional patent that MSU filed in the fall. You can patent these software mitigation strategies. There's existence proof for that. So we have about 8 months left on that provisional. If we can raise funds, we can go after a full patent on it. The second one is, all the software is copyright. MSU, with the license with MSU, they'll help kind of, track down and mitigate that a little bit. But you're right, people can go after it. The thing that we have in our advantage is flight heritage. So if you took RadPC and build a product, you can't claim flight heritage in the aerospace sector. They'd say, what are you doing here? So what we do is we say we've achieved flight heritage with our specific mitigation strategies. And so that's really the big thing. But you're absolutely right. It's a race to grow and try to capture as much market before somebody copies it down the road.
And just one follow-up, are those companies that you outlined as potential customers and or competitors, will they in-license the technology to use in their own platforms so they can brand it and move it forward into those associated agencies that are buying those products? So we become a licensee, or does Resilient sell the product per se?
So when you design these computers, there's a design environment where you type your code and you send it down to the computer. RadPC is embedded within that. So it's kind of like when you buy the software, you buy the RadPC plugin, and it's an IP core. So then you write your software, you enable RadPC, and then RadPC takes it from there and puts all this proprietary stuff around it so that when you implement it on your computer, it's radiation tolerant. And so that's kind of the model. And there's existence proof for that, like ARM processors, they embed themselves in design tools, and you can choose an ARM processor. So that's kind of our software approach.
So it's fairly high margin business, and I didn't see anything on the margins, but I assume it's fairly high.
Yeah, software IP companies tend to have pretty high margin, 60, 70%.
Okay. Thank you.
Bruce, go ahead.
So a very interesting product, actually. Question that I have, I'm trying to understand a little bit deeper. So what you have is basically these off-the-shelf FPGAs, and you just bunch of gates, and you got your software, and you built all kinds of redundancy. And if something happens in the field itself, it self-repairs and all that, right? So that's how you really get the cost down. The cost in today's computers isn't because they're rad hard, it's just because they don't have scale.
Yes.
It takes $20, $30 million to do a chip, and if you're selling only 1,000 of those, that's $200,000 a chip. So is that how you're getting there?
Absolutely. It's based on commercial off-the-shelf FPGAs. Right. So absolutely.
So those commercial off-the-shelf FPGAs, at some point, they're going to degrade because they're not rad hard. Question is, how much can you self-repair until that end of life? Does it last 20, 30 years, or eventually you run out of transistors that can repair themselves?
Yeah, it's a whole topic in itself, but the material degradation, it turns out that gets better as you use more cutting edge FPGAs. So smaller transistors, your material degrades less. So, but the faults go through the roof. So what happens is when you put these cutting edge FPGAs up there, they crash continuously. So it really becomes a problem of, we need to figure out how to mitigate the crashes, not so much the material degradation.
I see. Got it. Okay. Thanks.
Great. Thank
Very
you,
nice.
Bruce. Will or Ann, one of you have a question?
I have to say, this is all rocket science to me. Just kidding. Very intriguing. And I think the one thing I wanted to know, and you touched on a little bit, you talked about the two different sort of bookends of competition. Is there anyone else sort of trying to position themselves where you are, and what does that field look like?
Yeah, there is one company. There's not a lot of companies that do this, so it's like we all know each other. But there is companies there is one company in particular called Space Micro that probably has the most similar approach. And I know the owner, him. We've actually written SBIR grants together. So this is kind of our unique add to that. So we feel we want to focus on the computing part. So most aerospace companies, they kind of diverge and they start building technology all over the map. But what we want to do with Resilient is really focus on just the computing, because we want to provide that aerospace computer. And then instead of staying in aerospace, we want to take it and move it into critical infrastructure. So we do want to be aerospace because it's fun, it's awesome. But critical infrastructure is really where all the volume comes from. So the aerospace version is how we get off the ground and build a really hard computer and then move into the bigger market.
I know this might be getting a little off track, but I know even in like regular flight, there is a lot of radiation and just regular travel. Is this applicable even to the airline industry in general? Would this matter? Okay.
Yep.
You didn't touch on that in your market share at all, but I just was curious to know. Okay.
Yeah, so that's why Boeing is a potential contract. They've contacted me about, we want to use this because when you fly from San Francisco to Tokyo,
Right.
they say guaranteed to have a crash, at least one bit flip in your memory. So that would be a kind of a DoD style contract where they would take a variant of RadPC and we would build it for their particular use model.
And the grant that you get, is it expand, because you show that portion of your funding growing? Is that based on the size of the business? How does that expand with you over time, that grant?
So it's a phase one, 130K.
Okay.
That makes us eligible for a phase two, 750K.
I see.
And you can continue to get these. There's companies that
Right.
do this their whole career. So you could see one
Yes,
to
I
two
know.
phase twos at all times.
Okay. Thank you.
Great. Thank you. We're over time and I'm on Q&A. So I'm going to turn it over. Thank you, Brock. Thank you, Resilient Computing. And
Nice job, Brock.
thank you, judges.